Hi, so this week we will learn about the second part of brute force, which is about brute force algorithms for combinatorial problems. So in the last video, we already discussed about definition, advantages, and disadvantages of brute force, and also some brute force algorithms that are constructed based on related concepts and problem statement. So now in this video we will discuss about brute force algorithms that can be used for combinatorial problems and also show some exercises. So let's start with the brute force algorithms for combinatorial problems, which is also called exhaustive search. Exhaustive search is a brute force technique to solve a combinatorial problem which is usually used in combinatorial objects such as permutations, combinations, and subsets. The steps we need to follow to have an exhaustive search is first we need to enumerate or list every possible solution in a systematic way. We need to do it in a systematic way to make sure that we don't leave any possible solution. And also, after that, we need to evaluate every possible solution and store the best solution we found so far. If all our elements has been evaluated, we then declare the best solution. Although in theory we must be able to find a solution by exhaustive search, the time and resources needed to find the solution is so costly. So for problems with big input, exhaustive search is rarely used. There are some examples of exhaustive search, but in this video we will have two main examples that are traveling salesperson problem and also knapsack problem. So traveling salesperson problem is the problem where we have n cities and also their distance between each pair of the cities, and we want to determine the shortest path from one departure city such that all other cities are visited exactly once before returning to the departure city. So we can see traveling salesperson problem as a problem of finding a Hamiltonian cycle with a minimum weight. So a Hamiltonian cycle is exactly a cycle that visited each nodes in the graph exactly once. Well, except the initial node, because we also need to go back to that node in the end. For TSP, the exhaustive search steps are the first we need to represent the data of n cities and distances as a complete graph with n nodes. And then we enumerate or list all Hamiltonian cycle in the graph, and then we evaluate or compute the weight of each cycle, and we declare the winner, which Hamiltonian cycle has the minimum weight. So remember, we have three main steps for exhaustive search, which are enumerate, and then we evaluate, and then we declare the winner. So here's the example for TSP with four nodes and node A as the initial node. So here we need to find all possible routes we may have as the solution, and we need to find the weight or the total distance of each route. So the first possibility is route A to B, C, D, A, which has the total weight of 45. And then this route A, B, D, C, A with total route of 41. And then A, C, B, D, A with total weight of 32. And then A, C, D, B, A with the total weight of 41. The next one is A, D, B, C, A with the total root of 32. And the last one is A, D, C, B, A with the total root of 45. So we have six possible roots here. And why do we know this is the number of the possible roots we have? Because here we want to go from city A and we want to go to three other cities before we go back to A. So here we may go to B, D, or C. So we have three possibilities. And here we can go to either B or C or D, but who hasn't visited here. So there is only two possibility, and the last one only have one possibility. So in total, we have six possibilities. So that's why we have six routes here. And for TSP, remember that we want to find the minimum weight. So here we can see that 32 is the minimum weight we have here. So the shortest route is ACBDA and ADBCA of weight 32. For a complete graph with n nodes, there are n minus 1 factorial possible routes. So you can see here, like I said before, if I want to go to three other cities, then there is three factorial possibilities. If I add another cities here, then there are four factorial possibilities, and so on until we have n nodes. That means we have n minus 1 factorial possibilities. So yeah, in the previous case, we can see that we have six possible routes, and solving the problem by exhaustive search means that we need to compute the weight of each root in that n minus 1 factorial roots and find the minimum weight. The weight of the root with n edges can be computed in big O n, and the computation must be done in n minus 1 factorial times, such that the complexity of exhaustive search methods for TSP is big O n times n factorial, because here we have n minus 1 factorial possibilities where each possibility must be computed in big O n. So we just need to multiply them. However, we can improve the method by considering that half of the enumerated roots are the mirror of the other half. We can reduce the permutation by half. Like in the previous example, we can only consider three roots, this, and this. Back again to the previous example. Here, you can see that actually this one is the mirror of this one, right? This is they have the same weight, and also this one is the mirror of this one. You can see that they have the same weight. And the last one here is the mirror of 5, and you can see that they have the same weight. So basically we only need to compute 3 roots instead of 6 roots. Right. So here, to find the root, we can just say, let us only consider the routes where city B is visited before city C. So we can consider this route and also this route and also this route, right? Because the other three C is visited before we visited B, so we just need to consider these three so that we can also know the total weight of the mirror root of them. Okay, go back to this slide. With the improved method, we only need to evaluate n minus 1 factorial divided by two roots, but this means that we still have big O n square for the permutation, such that for graphs with large number of nodes, the improved method is still not efficient. Like for if we have 20 nodes, then we still have 9 times 10 to 16, 6 times 10 to 16 roots that are need to be evaluated. And unfortunately, in the sense of accuracy, there is no other algorithm do better than exhaustive search to solve TSP. So if you have a more efficient algorithm to solve TSP, they might not have 100% accuracy. And the next example is knapsack problem. And the problem is we are given an object and a knapsack, or maybe you know it as a backpack, that has a maximum capacity of k, where every object I has weight property wi and also profit property pi. And the question is which object should be put in knapsack if we want to have a maximum profit. Note that the total weight of objects that are put in the knapsack must be lower or equal to the maximum capacity of the knapsack. So this knapsack problem, we can see it as a problem of finding a subset from the set of all given objects so that the objects in the subset can be put in the knapsack and give a maximum profit. And the solution can be represented like this, where we have a set of n items, but we replace xi with 1 if the object I is chosen. It means that if it is put in the backpack, or 0 if we don't put it in the backpack. Such that in mathematics, we can see knapsack problem as the problem to maximize this function. We multiply profit and x for each items, and we have constraint that the total weight of what we put in the backpack is not larger than k. This is the steps for Knapsack problem. Basically, it's just like the other exhaustive search problem. Enumerate all possible subsets from the set of n objects, and then evaluate the total profit of every subset. But we also need to consider the constraint and also choose or declare a subset that gives us a maximum profit. For example, if we have n four objects and a knapsack where it has the maximum capacity of 16, then we have also the weight and profit for the four items. We want to solve the knapsack problem for this k and four items. To do that, we can use this kind of table where we have the subsets, which means the possibility, the possible solutions, and also total weight for each solution and total profit for each solution. This is the possible subset, where this means that nothing is put in the knapsack. This means we put only item 1 or the first item on knapsack and so on until this one means that we put all the items in the knapsack. So yeah, if we put nothing in the knapsack, obviously total weight will be 0 and the total profit will be 0 as well. And if we put only the first item, then we can see here the weight is 2 and the profit is 20. So that is the total weight and profit we have. And similar with others, And if we put two items, 1 and 2, then the total weight will be 2 plus 5, which is 7. And the total profit will be 20 and 30, which means the total one is 50. Similar with others too. And if we find a total weight of 17, which means it is bigger than the maximum capacity of the knapsack, it is an acceptable solution. So we don't need to count the total profit because we cannot have this as a solution. Yeah, and similar to others, such that uh, we have four unacceptable solution. Yeah, for knapsack problem, we want to find the maximum profit, so we just need to find the largest one here, and 80 is the answer. So yeah, the maximum profit is 80, which is given by the second and the third item. So we can write the solution like this. For an object, the number of subsets we need to evaluate is, yeah, so if we have n objects, 1, 2, 3, until n, mm, object 1 may be chosen or maybe not. Object 2 may be chosen or maybe not. Also with object 3, and so on until object n, which means for each object we have two possibilities, such that for all items in total we have 2 to n possibilities. Okay, so the number of subsets we need to evaluate is 2 to the n, and the computational of total weight for each subset can be implemented in, because we only need to add objects we choose. So object we choose is not more than n. It will be in big O(n). And the exhaustive search algorithm complexity for knapsack problem is this. We just need to multiply this and this. Okay. Both the SP and knapsack problem are example for exponential problem. Both problems are classified as NP problems or non-deterministic polynomial problems. So far, there is no deterministic algorithm that can solve the problem. Another example is in cryptography. This is a simple example. So exhaustive search in cryptography is an attacking technique to find the encryption key by trying all possible keys, and also known as exhaustive key search attack or brute force attack. For example, if we have DAS algorithm, which has the length of encryption key is 64-bit, but we only use 56-bit, and the number of key combinations that need to be evaluated is this much, because for each bit we may have 0 or 1, so the total possible keys are this many. And if for one trial we need 1 second, in the worst case where we need to try all the possibilities, then we need this many years to find the key, which is very costly. So there are some techniques to improve exhaustive search. One of them is called the heuristic technique, which is used to eliminate some possible solutions without the need to fully explore them. Heuristic cannot guarantee a solution, but can be used to solve many problems nicely. And even a good use of heuristic can dramatically reduce time implementation that is needed to solve a problem. For example, if we see an anagram problem, which is a problem of rearranging letters of a word or phrase to obtain other words or phrases that have different meaning. So, for example, if we have lift, we can rearrange them to devil, and also if we have tea, we can rearrange it to it, and also if we have charm, we can rearrange it to march. So, in exhaustive search, we just need to enumerate all permutation we have from these words we have here, from the characters we have here, and see if each permutation gives us a word that has a meaning or not. So that is the solution by exhaustive search. But in heuristic, we can make a rule. For example, that we can say that in English, letters C and H always used together as ch. So yeah, we can eliminate all words that are not use G and H together, C and H together. Yeah, there are some examples, combinatorial examples that can uh, be solved by exhaustive search. I will not go through these exercises until we find the, um, let's say, algorithm, but I will just show you how we can enumerate the problem, because really usually the main problem in exhaustive search is that people don't know how to enumerate the solutions, right? So here, job assignment problem, we are given we are given n people and n jobs, where every person will be assigned exactly one job, and the assignment of job J to person I costs Cij. And the question is, how should the assignment be done so that the total assignment cost is minimum? So how many enumeration do we have for this problem? So we have 4 jobs here, and each job will be assigned to one person. So there are 4 possibilities we have here, and 3 possibilities we have here, 2 for here, and 1 for here. So in general, we have n factorial possibilities. So for this problem, for example, we will have 4 factorial possibilities. And yeah, we just need to see if the person for each enumeration, what is the total cost we have with the given solution, and then we need to find the minimum cost we have from the all possibilities. And the next example is partition problem, where we are given n positive integers and we want to divide integers into 2 disjoint sets such that each set has the same total value. To be noted that this problem does not always have a solution. For example, if we are given these integers, we can divide them into 2 subsets, where each subset has value of 12 if we sum all of them, and also here we have the total value of 12. So how can we enumerate this problem? Well, this is basically the problem of finding a subset, a pair of subsets. So here, if we can enumerate subsets like usual, but for example, if one partition has no element, it means that the other partition have all elements, right? And then if one partition have one element, then the other partition have the rest of the element, right? So the problem is, the solution is every possible pair we have, possible subsets, pair of subsets we have. So we know that the possible subsets are 2 to the n, but for every subset we always have a pair, so we can divide it by 2. So we need to find all these possibilities, and then we can check if the pair has the total value for each subset or not. If yes, then it is the solution. But if all pair has no same total value of the subset, then there is no solution. The next example is magic square, where we are given a positive integer n, and we want to arrange numbers, integers from 1 to n square in a square of size n times n. So for like for example, if we have this, then we can arrange 1 to 9 like this, so that we have the sum of this column is the same with this, also the same with this, also the same here, the same with here, the same and the same and the same. So that is the problem. And how we could enumerate the possibilities. Basically, we just need to find all possible arrangement. Here there are 9 possibilities we have here, and then 8 here because one already taken, and 7, 6, 5, 4, 3, 2, 1. So the total is 9 factorial. So we will have n square factorial to for the enumeration. Okay, and here, yeah, for each possible solution, we just need to check if the sum of each row and each column and diagonal are equal or not. Okay, so here are the reference you can use for this topic if you want to read more. And the next topic will be greedy. And yeah, see you next time.